Hi everyone. So we're going to talk today about irrational numbers, and more broadly we're going to talk about the real number system. So we're on lesson 2, page 4 of your notes. So please make sure that you have those out and just fill them in as we go along. Okay, so the real number system is basically a way that we categorize and organize all of the numbers that exist in our world, which are called the real numbers. Okay, so what I'd like to do first is to just define all of the different categories. And in math and set theory, we call those categories sets of numbers. And then we will use a Venn diagram, which is a graphic organizer, to show how they all fit together and the relationship between all of the different sets. Okay, so the real number system. Real numbers are all of the numbers that exist in our world. We use the abbreviation, whoops, I'm on the eraser. There we go. We use the abbreviation R with a double line through it like that to talk about all real numbers. And I'm going to talk about the most specific set first and then work my way outwards. Okay, so the most specific set of numbers within the real number system, those are called the natural numbers. And we can use the letter N to abbreviate that. And natural numbers are also called the counting numbers. And the reason for that is that if you started to count objects, what would you start with? You'd start with 1 and then 2 and then 3 and then 4, etc. And that's exactly what the natural numbers are. So 1, 2, 3, 4, 5, etc. until infinity. Okay, so that's the natural numbers. The next set that I'm going to talk about are the whole numbers. And we can use the letter W to abbreviate that. And the whole numbers basically are the natural numbers, but instead of starting at 1, we start at 0. Okay. And sometimes people ask, why do we have both, like the two sets instead of just one, because they're very similar. I don't have an exact answer for that, but what I can tell you is that 0 is actually a relatively new number in the history of numbers. And the reason is that thousands of years ago, people used numbers basically to count objects that they had. So they would count their sheep in the field, and there was no reason to start at 0. They would just start at the first sheep. And when 0 did emerge at various points in history in different civilizations, it was actually quite controversial. Okay. All right. So the next set is the integers. Okay. And we can use the letter Z. That's sort of the technical one, but you could also use the letter I to abbreviate the integers. And integers are positive and negative whole numbers. So take all of the whole numbers, we take the positive ones, but we can also make the positive ones negative. So like -3, -2, -1, 0, 1, 2, 3, and then it continues in both directions. Okay. Rational numbers. The letter that we use for rational is Q. Rational numbers are defined as any number that can be written as A over B. Okay, so a lot of people, when they think of a rational number, they think of a fraction. And that's why we have this A over B. There are some restrictions, though, on A and B. So A and B are both integers. And additionally, B cannot be equal to 0 because we can't divide by 0. When we divide by 0, we get an undefined value. Okay, so some examples would be something like 3 over 4. That's obviously a fraction. 3 and 4 are both integers. Something like negative 0.222, etc. Okay, so when you have a repeating decimal, all repeating decimals can be written as fractions. This is actually equal to negative 2 over 9. All right. Another example, let's look at maybe the cube root of negative 64. Okay, so this looks like a radical, but we can write it as a whole number, or sorry, not a whole number, an integer. This is equal to negative 4. And of course, any number can be written as a fraction if you make the denominator a 1. Okay, so that's another example. What else? Oh, if you have a decimal that terminates, that ends, something like 0.4. Okay, 0.4 is 4/10, so you can write that as 4/10. And then, of course, reduced, whoops, this would be 2 over 5. Okay, all right, so those are the rational numbers. Irrational, I'm going to move up here because I'm running out of space. So irrational numbers. Okay, irrational numbers uses this symbol. It's a Q with a little hat on top. And the hat in set theory means not. So essentially we're saying not Q, not rational. Okay, and this has the opposite definition to rational numbers. So any number that cannot be written as A over B, where A and B are integers. I'm going to use the symbol for that. And B cannot be equal to 0. Okay, so an example of an irrational number, probably the most famous one, is pi. And a decimal approximation to pi, 3.1415926, and it keeps going and going forever. Okay, so pi is a non-terminating, non-repeating decimal. Okay, it doesn't terminate, doesn't end, and it doesn't repeat. That means it's irrational. We cannot write it as a fraction. Okay, other examples. Well, a ton of radicals are irrational. So any square root of a non-perfect square, like for example, the square root of 8. 8 is not a perfect square. Therefore, the square root of 8 is not rational. Okay, cube root of a non-perfect cube. So the cube root of 25, for example, not going to be rational. All right. Now, I told you guys that we were going to organize these into a Venn diagram. I'm just going to kind of clear this space here. Okay, so here's our Venn diagram as to how these all fit together. Okay, so our Venn diagram is going to be this box, and this box is going to represent the real numbers. Okay, now the real numbers are divided into two categories. There's a real number can either be rational or irrational. So I'm going to make a line to divide my Venn diagram in two. One of those is Q, and one of those is Q naught. Okay, now it looks like Q is bigger than Q naught, but in fact it's not. There are actually more irrational numbers than rational numbers. So in a Venn diagram, the size of each region in the Venn diagram does not necessarily correspond to the size of the set. All right. Now within the rational numbers, we have more specific sets. So all integers are also rational. So they need to go in here. Whoops. Integers can all be written as fractions, right? So these are the integers. Within the integers are all the whole numbers. All whole numbers are also integers. So the whole number set is actually contained in the integers. And then, of course, all natural numbers are also whole numbers. So natural numbers are the smallest set, and they go right there. Okay, so you may guess now why I made the rational side bigger than the irrational side. It's because I had more, these are called subsets, sets of sets to fit into that side. All right, and this is basically a graphic organizer that shows the relationship between the sets. So for example, if I'm considering a natural number is also a whole number because it fits in that set. It's also irrational because it fits in that set. And it's also an integer rather because it fits in the Z set. And it's also rational because it fits in the Q set. And then of course, it's also in the rectangle of real. So a natural number is a real number. Okay. On the other hand, if I'm looking at an integer, that's not necessarily a whole number because whole numbers do not cover the entire bubble of integers. Okay, so an integer may be whole, like the number 5 is whole, but the number -5, on the other hand, is not. Okay, so what we're going to do is look at a couple of different numbers and basically just say first whether each number is rational or irrational. That's sort of the most important distinction to make. Okay, and then we're going to say, how do we know? Well, the number -3/5 is written in the form a over b. Whoops, I forgot an e there. Where a and b are both integers. So this is rational. Okay. The square root of 14. Well, 14 is not a perfect square, right? It's between 9 and 16, which is 9 is 3 squared and 16 is 4 squared. So this is going to be irrational. And why 14 is not a perfect square. Okay. C, the cube root of 8/27. So if we're taking the cube root of a fraction, then the numerator and the denominator both have to be perfect cubes. And in fact, they are. 8 is 2 cubed and 27 is 3 cubed. So this is rational because it can be written as 2/3. Okay, so C is rational. Okay, all right. Let's look at this example as well. So the square root of 49/16. Well, we're taking a square root. 49 and 16 are both perfect squares. So this can be written as 7/4. So this guy is rational. Okay. B, the cube root of -30. So we have to ask, is -30 a perfect cube? And it is not. Okay, so this is going to be irrational. And the reason is -30 is not a perfect cube. Okay, and 1.21. This is a terminating decimal. Terminating means that it ends. All terminating decimals are rational because they can all be written as fractions. So you can actually think of this number as 1 and 21 hundredths because this 1 at the end is in the hundredths position. So this can be written as 1 and 21/100. So that's a mixed number, or 121/100 would be an improper fraction. Either way, both of them are fractions, so this is rational. Okay. All right, we're going to turn over the page and try some more questions. So what we're going to do next in this example is classify each number. And to classify each number, I want you to tell me all of the different sets that each number belongs to. So a number may belong to more than one set, right? So for example, the number -3, that's an integer, but it's also a rational number and it's also a real number. So that would belong to 3 sets: integer, rational, and real. It's not a whole number though, so we can't say that it's part of that set. Okay, so -6. -6, and by the way, you may, I don't know if I have room to fit it in, but I'm going to try, want to actually just have this handy while you're doing this. So this is Q, Q naught. And then in here we have first the integers, then the whole numbers, then the natural numbers. Oh, I just fit it. And of course, this whole Venn diagram is the real numbers. Okay, so you want to start with the most specific. -6 is an integer. It's not whole because it's negative, but it is an integer. And so it belongs to Z. It also belongs to Q because Q is within Z, Z rather is within Q. It's rational. And it's also, of course, a real number. Okay. The number 42. Well, 42 is a natural number because it's like the counting numbers, 1, 2, 3, 4, 5, etc. So this is natural. Natural is within whole, so it's also whole. Whole is within integer, so it's an integer. Integer is within the rationals, so it's also a rational. And it's of course a real number as well. Okay, 3/4. 3/4. So 3/4 is not natural, whole, or an integer because those don't have like parts of a number, right? So this, for example, as a decimal would be 0.75. So it can't be a part of a number, but it is a rational number because it is written as a fraction. So it belongs to those two sets. Okay, -1.5. Well, that's like -1.5 or 3/2, -3/2 rather. Okay, so this is not, again, natural, whole, or integer because it's not an entire number. It's got a part of a number as well, but it is rational and it is real. Okay, the square root of 12. Well, the square root of 12 is not a perfect square. So this is going to be irrational. Irrational numbers are still real though, so we can add that set as well. Okay. Negative square root of 64. Square root of 64 is 8, so negative square root of 64 is -8, which can be written as -8/1. It's also an integer because it's a negative whole number. So this is going to belong to the integers, the rational, and the reals. Okay, 1.121212, etc. Okay, so this is a non-terminating number, but it's a repeating number. The decimals repeat. So this is in fact rational. It's actually to figure out the fractional part, you take the repeating part, which is 1, 2, and put it over the same number of 9s. So this number is 1 and 12/99. Okay, so it is rational and it is real. Okay, 1.123, and that pattern continues. So it would probably be 4, 5, 6, 7, 8, 9, and then 10, 11, etc. Okay, so this is a decimal that's non-terminating. There is a pattern to the decimals, but it's not a repeating pattern. It's not a repeating pattern. So to be rational, it has to be repeating. This is an irrational number. It's also real though. Okay, and then finally, we've got 3.23233, etc. So this guy also doesn't terminate, and it doesn't repeat though. There is a pattern, right? So what you can see is that it's 2, 1, 3, 2, 2 3s, 2, 3 3s. The next would be 2, and then a segment of 4 3s. Okay, so there's a pattern, but it's not a repeating pattern. So this is irrational and also real. Okay. So that's basically what I want you guys to know about the real number system. It's especially important to be able to tell whether a number is rational or irrational. Making that distinction is probably the most important thing. And being able to justify. All right. Now, to justify that something's rational, all you need to do is show that it can be written as a fraction. I do want to today, though, add a little piece on prime factorization because we are going to need this as we move forward into tomorrow's lesson. And this is something that you probably have seen before. A lot of people don't remember it, though, so I want to give you a little refresher. Okay, so first let's start out with some definitions. Prime factorization. So a prime number is a number that has exactly two factors. One and the number itself. Okay, so it's got to have exactly two factors. Factors are numbers that divide another number evenly. So for example, 2 is a factor of 8 because if you go 8 divided by 2, you get 4. You get a whole number. Okay, so some examples of prime numbers. Numbers that only have two factors. Well, 2 is prime because the only factors are 1 and 2. 3 is prime. Only factors are 1 and 3. I'm just going to write the first few out. There are actually infinite prime numbers in the world. 17 is prime. 19 is prime. 21 is not because it's got other factors, 3 and 7. 23 is prime though. 29 is prime, 31 is prime, and I'm just going to do ... Okay, so that's the first couple prime numbers that exist in the world. A composite number is a number that has 3 or more factors. Whoops, maybe I'll erase that. Number that has 3 or more factors. Okay, so for example, the number 10 is prime because the factors of 10 are 1 and 10 and also 2 and 5. So it's got other factors besides for 1 in itself. Okay, so that would be an example of a composite number. Now, one thing that's interesting is that 1, the number 1 is neither. It's neither prime nor composite. And that's because it doesn't fit either definition. Prime number has to have exactly 2 factors. Well, 1 only has 1 factor, and a composite number has to have more than 3, or 3 or more rather. And of course, 1 only has 1 factor. So 1 is sort of in a category of itself. Okay, now prime factorization is the process of breaking down a composite number into the product of primes. Okay, so composite, you can think of prime numbers actually as like building blocks, like almost like little Lego pieces. And every composite number is built out of those Lego pieces. So when we are doing prime factorization, we're breaking that. You may put a couple Lego pieces together, and then we're breaking those down into a product. I mean, we're multiplying together. So for example, the prime factorization of 10 is 2 times 5. Okay, because 2 and 5 are both prime. Now, sometimes this is easy to do in your head, but sometimes it takes a little bit of work. So we are going to, I want to demonstrate to you how to do that. So let's start with, let's see. just as an FYI, I'm recording right now and I have a dog and a child that just walked into the room. So you guys may hear some background noise. Hopefully it's not too bad. Okay, so let's say, for example, we want to do the number 24. And we want to break that down into the product of primes. Well, as a start, you could just find two numbers that multiply to 24. Okay, and I'm going to do this two ways. I'm going to do it using a tree and a ladder. Okay, so 24. Well, 2 is prime, so I can break it down as 2 times 12. Okay, and the idea with this is that if one of the ends of the two branches is prime, that branch ends. So 2 is prime, so that's going to end. 12 is not, though. I can break that down further. I can break that down into like 3 and 4 maybe. 3 is prime, but 4 is not. 4 can be broken down into 2 and 2. Okay, and then 24 is going to be equal to all of the ends multiplied together, 2 times 3 times 2 times 2. Now, I like to, when I'm writing out prime factorizations, I like to write the primes in order from least to greatest, just because it helps me to organize them. Okay, you can also do something called a ladder. This is a tree. I actually prefer the ladder personally, but you can use either. So a ladder basically works like this. You put the number over here, and then you draw almost like an upside down division sign. And the rule is that all of the numbers that are on the left have to be prime. So for example, 2 is a factor of 24. And then the quotient, when I go 24 divided by 2, I end up with 12. And the 12 goes down here. And then you continue the ladder until the number at the bottom is prime. Okay, so 12 can also be divided by 2, and 12 divided by 2 is 6. And then I'm going to do 6 can also be divided by 2. 6 divided by 2 is 3. And then I stop because the 3 at the bottom is prime. Okay, so 24 is equal to 2 times 2 times 2 times 3. Or you can also write the repeated primes in exponential form. So it's equal to 2 cubed times 3. Okay. All right, let's try one more and then we'll end for today. Okay, let's see. Let me think of a number. Let's take maybe the number, let's see, 5,640. Okay. All right. So if we're going to do the tree, well, I always start with the smallest primes, which are 2. 5,640 divided by 2. This, you may need to use a calculator to do it. Let me think. 56 divided by 2, 22. Okay. So 5,600 divided by 2 is 2,800, and 40 divided by 2 is 20. So 2820. I hope that's right. Okay. Now I'm going to keep going. So this is also a even number, so it can also be divided by 2. So I'm going to keep going on that 2. Maybe I'll circle this because that's prime. And 2820 divided by 2 is 1,410. Okay, and then this is also even. So when I divide this by 2, I'm going to get 705. Okay, now 705 is not even. So that's the end of my 2's, but I believe it's divisible by 3. So I believe that when I divide this by 3, I get 135, because 600 divided by 3 is, 235. 200, and then 105 divided by 3 is 35. So this should be 235. 235. Okay, I just made this number up, by the way, so I'm kind of putting myself on the spot here, but anyway. Okay, so 235 divided by, this is divisible by 5. So 200 divided by 5 is 40, and 35 divided by 5 is 7. So this should be 47. And 47 is prime. There we go. Okay, so you could also use a ladder, of course. So I always start with the smallest primes and then exhaust those till I can't divide by that anymore and keep going. So this is divisible by 2. This divided by 2 is 28, 20. Then I divide that by 2 and I get 14, 10. I can divide that by 2 and I get 705. And then I can divide that by 3. By the way, you don't have to do this in your head. You can take out a calculator and just test things out as well. And this is 235. And then I can divide that by 5 and I get 47. And 47 is prime. Okay, so written out using prime factorization. I have very little room, but I'm going to squish it in. 5,640 is equal to 3 2s, so 2 times 2 times 2, a 3 times 3 times 5 times 47. Or 2 cubed times 3 times 5 times 47. Okay, so I am going to end with that today. We will be using prime factorization in tomorrow's lesson though, and I will see you guys then.